Hello, my name is Jacob. Welcome back to the Introduction to Saint video series. In this example, we will show you how fun and easy it is to simulate balanced AC power flow in Saint. Let's open the same network from the intro video. The model we are using is freely available via the links in the video description. Recall, this network has electric lines and transformers laid out over New England. From the map legend, we see that all the base voltages of these lines are 345 kV. Balanced AC power flow simulations require positive sequence reactance, resistance, and susceptance branch property values. Users can either define per length or per unit values for these properties. For example, this line in southern New Hampshire has a reactance of 0.0323 per unit. Zero sequence properties are only necessary for unbalanced AC power flow and will be covered in a separate video. If we zoom in, we see a transformer. With the node bar, I can see what this transformer connects: the Vermont Yankee nuclear generator. Let's open an AC power flow scenario to study how power flows throughout this network. This network is based on the IEEE 39 bus system, and this scenario is configured to reproduce the loading on that test network. This scenario is configured with events that set certain power flow conditions. Let's look at the events for our Vermont Yankee generator. These three events define how this generator will operate in the steady scenario. The parameter column shows that this event defines the voltage magnitude set point. This event defines the active power set point. This event defines, as a weighted sum, how much this generator will deviate from its active power set point to compensate for unmet demands or losses in the system. The value column shows that these events are set to default values. Let's execute our scenario and observe the response of this generator and the others on this system. Let me pin some columns to help me assess the active power output. Because of the events we just discussed, 9 of these generators are operating at their active power set points. However, Bridgeport is not. This is the only generator with a non-zero participation factor set point, which configures it as the slack bus. Let's configure Vermont Yankee to participate in the slack of this system by changing the corresponding event value. And let's execute this scenario again. The change in the event value is reflected for the new PF set value. Now, both Bridgeport and Vermont Yankee deviate from their active power set points, compensating for slack in the network. We encourage users to investigate how voltage set points can be changed using the VMset event. Now let's open the AC power flow peak demand week scenario. For this hourly resolution scenario, the active power dispatch for all the generators is the result from the optimal dispatch calculated by the production cost scenario. For more details on the production cost scenario, please see our other intro video to production cost optimization. We can see that 3 generators will compensate for the resistive losses not captured in the production cost scenario. By setting the participation factor equal to their capacity, this is a proportional compensation. Let's execute this scenario and clean up our workspace. Looking at the dispatch plot for this whole week, the generator output is greater than the demand to compensate for losses. The 3 generators from the events before are making up this difference. Let's see how Vermont Yankee is operating. It remains fully dispatched during this week because it has the lowest variable operating cost. It is maintaining its voltage set point by sourcing and sinking reactive power at different hours throughout the week. Let's compare this behavior to a generator at the edge of the network. At this node, the voltage is not being held static. Let's see what the generator is doing. It's clear from the active power plot in blue that this generator is being turned on and off. Consequently, the voltage changes when it's unable to regulate. Now we can animate the system. We can see how voltage values and power flow directions are changing throughout the week. In this video, we explored the necessary properties and setup of AC power flow simulations, explored how slack is distributed with a participation factor, investigated the AC power flow response of a system with a dispatch determined from a production cost optimization, which is a valuable generation transmission workflow. Thank you for watching our video on balanced AC power flow simulation. Hey there, just a reminder to check the video description for links to helpful resources like the model used in this video, other instructional videos, documentation, and our Saint user forum.